So let's start with our wall up here. Let me draw this again. And what we want to do is we want to take some differential control volume. So we'll take a slice here. And we're going to do our typical control volume analysis. So this is going to be our position x. And we're going to have q dot x coming in. We do have q dot x plus dx leaving. We don't have any generation, but we do have internal energy storage here. So that would be partial u with respect to time. And then we're going to note that everything is, t at time equals 0 is equal to t initial, for all positions x. So that's our control volume. We then do our energy balance, as we've done many times now, and that becomes q dot at x is equal to q dot x plus dx plus partial u with respect to time. Expand that out and cancel things, and we end up with 0 is equal to partial q dot partial x dx plus partial u with respect to time. But I'm just taking this term saying it's q dot x plus dq dot x dx times dx, this thing here, and then this carries along. Okay, so we need expressions for these two terms. Q dot is going to be Fourier's law. So Q dot is going to equal minus K AC partial temperature with respect to position. And then U is, let's see, du, dt. That is, so that's mass times specific heat. So mass is going to be density times the cross-sectional area AC times dx, right? AC times dx is my volume. So rho AC dx is mass times specific heat times partial of temperature with respect to time. So I can bring those things together and note also that alpha equals k over rho c. And then you end up with the expression alpha d squared temperature dx squared is equal to d time, or d temperature d time. And then we would write what the boundary condition, so t at time equals 0 is equal to t initial. And we know that t as x goes to infinity is equal to t initial. Right? Let's just stop and make sure that that makes sense. So we have our initial time condition. We have one boundary condition where I'm saying if you go far enough out in x, I know the temperature. So I don't actually know the temperature at any specific position. I just know if you go far enough, it's this. So that's a valid boundary condition. Right? The other boundary condition was the convection one. And the convection one is just what? H bar t initial plus beta t minus t at x equals 0 is equal to minus k partial temperature with respect to x at x equals 0. Okay, so this is my statement of the problem right here. Questions on that? Okay. We have the statement. What's our job now? This is all again for Laplace. So we're going to take this and make it transformed into the Laplace S domain and then work with it there. Noting again, we have the thing that's different now is we have time and x appearing in this solution. That's the new thing. So looking at our reminding ourselves of the steps and then the problem statement, we've got to, step 1. We need to transform to complete that step. So let's go through and make the transform here. The first part would be, where do we want to start? So the first part is going to be taking the transform of that second derivative term. So if we look at our table, that just becomes the partial squared of t hat, which is a function of x and s now, over dx squared. And then we're bringing the alpha over to the other side, so that's 1 over alpha times, what's the transform of the right-hand side? So that's d temperature, d time, and that's the second thing, or the third thing in the table there. S, t hat of s minus the initial condition. So that is s t hat of x and s minus our initial condition, which was just t initial. So again, we've enforced the initial condition at this point. This is now an ODE, or a PDE, right? And I want to maybe make a point that's a little bit source of confusion. So I've told you if we have a PDE, you can do this and get to an ODE. And then I'm writing it here as a PDE. I'm doing it this way, one, because it's written this way up here. But when you're doing this transform, you can actually think of S as not its own independent variable. You can think of it as closely tied to time. And so really what we have is just a function of x, right? So because S is this kind of quasi-constrained variable, I could equivalently write this, and I think I will just for the sake of being correct, would be d as in the ordinary differential equation. So you see that there's this S relationship here, but really in the S domain, what we're concerned with is these independent variables. So x is independent. It's kind of a confusing point, but we're now at the point where we have an ODE and we can solve this. So I could look at this and I see, okay, I have a second order derivative, I have a temperature that could come over here, and then I have some stuff left over on the right-hand side. This is just a non-homogeneous ODE, and we can solve that using the same methods we've used for the other non-homogeneous ODEs. For the sake of time, I won't walk through that process completely, but I will tell you that if we break this into t is equal to th plus tp, th, I should say t hat. This is still in the S domain. So t hat of h is the following. That is c1 exponential the square root of s over alpha times x plus c2 exponential of minus square root of s over alpha times x. That's our homogeneous solution. You just go through the process. The particular solution for this is, let's see. So t hat p ends up being t initial over s. So this is the solution that we would get through just going through the same process that we've done multiple times. So now we have our solution in the S domain. Or you just add those back together. That's our solution in the S domain. So that's check for step 2. Then we have to go back and do the Laplace transform. Let's see, how much time do we have left? OK, let me cover one more thing before we wrap up, and then we'll call it good for the day. So we need to go back, but we also need to note that this solution here has these two unknown coefficients. Right? These are actually unknown boundary condition coefficients. We need to enforce the x boundary conditions. And in order to do that, we have to enforce them in the S domain. Okay? We have to go through and then take all the x boundary conditions, express them in the S domain, and enforce them there. So let's do that as our last thing here. Our boundary conditions, let me move on to the next page here. So our first boundary condition was this t as x goes to infinity is equal to t initial. This one here. So if we look at that one, let's see, and transform that in the S domain, that becomes t hat as x goes to infinity is equal to just what's the Laplace transform of this thing here? I think I heard it, T initial over S. Okay, so that's the Laplace transform of that. So I would take that and then let's enforce this boundary condition. Well, that's good. So we're going to do that next. Next time we'll go through and enforce these boundary conditions. We'll take the other one. But yeah, what we'll end up with is solving for those constants in this domain, and then we can go back from there.